Welcome everybody. This is our seventh video in question bank slash numerical series for chapter magnetic effects of current of class 10. Till now we have made around 6 videos in question bank series and around 6 videos for theory part of this chapter. If you have not checked them out, then you can find them on our YouTube channel. The name of channel is Point Basics, and the name of the playlist where you can find them is class 10 physics. And as usual, if you find them these videos useful and valuable to your study, then please like, share and subscribe, because your like, share and subscribe act as a motivation for us, and it also act as a feedback for us that we are doing something meaningful. So please do like these videos, share these videos, subscribe to our channel, and if you have any valuable suggestions, then please put them in the comment section. If you have any doubts also, you can put them in comment section. We will try to resolve them at the earliest as possible. And with this, let's start today's video. In today's videos, I will be starting our third exercise. Till now we have completed two exercises, and in two exercises in combined we have completed around 70 questions, even more than 70 questions. And today's video we will start our third exercise. This exercise is also going to have around 30 questions. So in it as a whole we will be completing around 100 questions for this chapter, which I mentioned previously, and we have done the same for other chapters also, so you can also check them question bank series for those questions. So let's start today's video. So this is our today's question series. Let's start with question number 1. So in question number 1, it is mentioned that if a current in a wire is flowing in the vertically downward direction and a magnetic field applied from west to east, what is the direction of force acting on it? Now, as let us first draw the directions. Considering whenever you draw directions, you should use this as your standard, that this is your north, south, east and west. So from this, and we when we draw normal directions, xy direction, this is x, y and z direction. So now we know if our magnetic field is applied from west to east, means magnetic field is going from west to east, so it is going in positive x direction. So magnetic field direction west to east, or going in positive x direction. Okay, now if current wire is flowing vertically downwards, now current is flowing vertically downward means suppose if you have to visualize this whole concept, then you can consider your rooftop fan. It is attached to your roof via a long cylinder. That cylinder you can consider as a conductor in which current is flowing downward, and for that east to west, west to east, there is a magnetic field. Suppose you have a pen in your hand, and when you hang that pen vertically downward, then that pen represent your conductor, and current in it is going downward, and your magnetic field is flowing from west to east. Okay, so your force can be when force act on this conductor, it can act on either in north side or left side depending upon whatever the direction we conclude using formulas. So let us find the direction, that what will be the direction. So according to our xyz, our conductor will be in z direction because conductor is coming out of the screen or perpendicular to east to west. So value of current will be in, as value of current is going downward, so current will be in minus z direction. You can also visualize this like this. If we consider east to west, suppose again you have a pen in your hand which is hanging freely. Now your east to west, if your east to west is x direction, then your north to south is y direction. Okay, and your pen is perpendicular to both of them, then your pen is in z direction. And as it is going down, current is going downward, so it is current direction of current is downward, so it is in minus z direction. So your east to west, or your west to east is x direction, north to south is y direction, then your freely hanging pen is in z direction, or and current is going down, so it is in minus z direction. Now we know that force is on a current carrying conductor is bin sine theta, and direction is decided using direction of length and magnetic field. And we know that direction of length is same as direction of current, so direction of length is minus z, and that of magnetic field is x direction. It is minus z, it is x. And when you use it, solve it using our direction method, x y z, then you find you are going z to x. We can add a bracket here. When you go z to x, you are going clockwise, so you will get y, and there is minus, so force will be in minus y direction. Minus y means in south, so force will be acting towards south direction. Now this is using our mathematical method. Now we have to find using also, which is in your syllabus, that is Fleming's, using Fleming's left hand rule. And we have already discussed the rule that your thumb denotes force, first finger denotes field, magnetic field, and second finger denotes current. Okay, this is second finger, this is first finger. Now you have to orient your hand such that your left hand such that your thumb, your first finger and second finger are perpendicular to each other. And now, as we know, field is going west to east. So according to this diagram, field is going, here is left of the screen, here is right of the screen. So field is going left of the screen to right of the screen. So your first finger will be pointing towards the right of the screen, and this is field. Now current is going in minus z direction. Your second finger or your mid finger gives the direction of current, so your second finger should be going into the screen. So your second finger will be pointing towards the screen, and your first finger will be pointing towards right of the screen. Then you will find that your thumb is pointing downwards, and downward is minus y direction and south, and we get the same result as we got from this. So you can use both of these methods and find out the direction of force applicable on the wire. Now let us solve the second question. When do we apply Fleming's left hand rule and right hand rule? We have to find both of these. So we have already discussed this. Left hand rule is applicable when we have to find direction of force acting on a current carrying conductor. And right hand rule, and this is Fleming's right hand rule. There is another rule also known as left hand thumb rule, that is different, and this is Fleming's right hand rule, and this was Fleming's left hand rule. So with Fleming's right hand rule, we find direction of induced current in a conductor. So this is the answer of second question. Now moving to question number 3. How much force is exerted by a magnetic field on a stationary charge? Now we can solve this via two methods. First is, we know that force on a charged particle is QVB sine theta. Now if it is given that stationary charge, so stationary charge means velocity is 0. So if you put velocity 0 here, so force will be 0. This is by using formula for force on charge particle, but you don't have it in your syllabus as per mentioned. So we have another formula which is mentioned in your formula in your syllabus. It is according to your syllabus, that is BIL sine theta. Now if charge is stationary, it means there is no current. It means I is 0, and when you put I is equal to 0 here, then you get F magnetic is equal to 0. So there is no force on a stationary charge particle in magnetic field. And also if a particle is moving, but it should also have some charge, because current only occurs when there is a charged particle moving. If there is a neutral particle is moving, then there is no current. So for force to act, there should be a charged particle, and that should move. If neutral particle is moving like neutron, then there will be no force acting on it. So let's move to question number 4. A positive charge is moving vertically upwards when it enters a region of magnetic field directed towards north, in which direction force on the charge. So again we will use our same method. This is north, south, east, west, and all these directions are in the plane of screen or in plane of paper on which you are writing. And if conductor is charge is moving vertically upward, so it is moving in z direction. It is moving perpendicular to both of these. It is moving like this, perpendicular to all of these. Here angle is 90, here angle is 90. Okay, so if you draw directions, this is our y direction, this is our x direction, and our perpendicular direction is z direction. So charge is moving in z direction. So velocity is in Z direction and magnetic field is towards north. So magnetic field is towards north and north is in Y direction. So direction of B is Y direction. It is a positive charge. So we know that when electrons flow, so if they are flowing from west to east, as they have negative charge, so direction of current will be from east to west. But if a positive charge flow from west to east, then direction of current will be the same. For positive charge, direction of current is same, and for negative charge, direction of current is reverse, in which the negative charge is following. So here positive charge is flowing in Z direction, so direction of current will also be in Z direction. So now we have to find the force. So force depends upon direction of current and direction of magnetic field. Actually here direction of length comes, but direction of length is same as direction of current, so that's why I write direction of current. Now direction of current is Z and direction of field is Y, and using our old formula x, y, z, you can find out. You are going z to y, we are going z to y, and it is reverse. It is anti-clockwise, so we are going anti-clockwise, so we will get x, but x in negative, so answer will be minus x. So force will act in minus x, or in this direction, or in west direction. So force will be acting in west direction. So this is why this was using our mathematical formula. Now we have to use Fleming's left hand rule. So as we know that current is in z direction, so your finger should be your second finger for Fleming's left hand rule, which denotes the current, should be pointing towards the roof, and field is in y direction. So your y direction towards is north. Here your y direction is towards north. So your second finger, first finger should be pointing towards the north, and from this you will find out that your thumb is pointing towards the west direction. Your second finger or your mid finger should be pointing upward because current is going upward. Your first finger should be pointing towards the north direction, and then you will find that your thumbs points towards the west direction, or here we have denoted as minus x direction. So this how using this Fleming's left hand rule you can also find out the direction of for acting force. Let's move to next question, question number 5. So question number 5 is two circular coils A and B are placed close to each other. If current in coil A is changed, will some current is induced in the coil B? Give reason. We have already explained this phenomena in our bonus video, and yes, the answer is yes, there will be some current induced in second coil. This effect or this phenomena is known as electromagnetic induction. where changing current in first coil induces current in second coil. You can also draw a diagram for this, and for showing the diagram, what you can do, let's have a soft iron rod. It is necessary for doing this. Now have a first coil here. This is our first coil. We have connected it to battery so that a current can flow in it, and then have a second coil. This is our second coil, and here we attach a galvanometer with this. And what happens in this process, I have already explained in detail in our previous question videos, in previous question series videos. So you can find out that whatever happens, and if you have still any doubts, then you can ask in comment section. I will try to solve them. I have also explained it in our bonus video, so you can also check out there. Moving to question number 6. Why do we connect earth wire in a house? Give 2 reasons. So we have already covered this in detail in our previous video. The main reason is that whenever short circuit happens, then earth wire prevents earth wire gives a low resistance path for current to go into the ground, and that's how it prevent us from getting, us means us humans, from getting that shock. Because suppose this is your electrical instrument and it has some wires inside. Now this is our mains wire, this is our neutral wire, and this is our earth wire. If some short circuit happens here in the instrument and instrument's entire body gets some current, suppose some current start flowing on instrument's body, then this green wire, which is connected further to earth, gives this current a path to move into the earth. So this whole current moves into the earth like this through this wire, and we are mm, saved from any type of shock which could have happened to us if this wire is not there. So that's why the earth wire is necessary. Now, what type of current is used in household supply and what type of current is given by cell? We have already covered this type of question. And in household supply, we use AC current, and in cell, we have DC current. The frequency of AC current in India is 50 Hertz. So it changes its frequency, its direction 100 times per second. Frequency of DC is 0 Hertz and it does not change its direction anytime. It starts and stops always in same direction. For AC, this is not same the case. AC changes its direction after 1 by 100 second each time, or 100 times in a second. And mainly AC is used for transmitting the power. And why AC is used, we have also discussed in our previous video. You can also find that out. Moving to question number 7. To which wire do you connect fuse wires in a household circuit? Write the names of the one source of AC current and one source of DC current. So which wire is used to connect a fuse? Always mains wire or live wire is used to connect to the fuse. And now coming to the sources of AC and DC. So source for AC is our transformers, our electric power station, and our UPS inverters. They all provide us AC electricity. And for DC, we have batteries. We have sulfur acid batteries and lithium ion batteries, which are used in our mobile phones and your laptops, etc. So these all, using these all, we get direct current or DC. And using transformers, electric power stations, and UPS and inverters, we do get AC power. So with this, question number 7 is complete. Moving to question number 8. So in question number 8, we have to discuss when a magnetic compass, how it behaves when it is placed near a current carrying conductor. So we have discussed similar question already. So it will be in brief. So suppose we have a conductor like this and it is carrying current in from bottom to top in upward direction. Now give it some connection with the battery and a resistance R. So here is resistance, here is battery. Current will flow from positive to negative terminal. So wait a minute, we have to reverse the direction of battery. So let us reverse, and direction of current will also be reversed accordingly. So this is our battery connections. This is negative, this is positive, and now this is the direction of current. Now if you use right hand thumb rule, then you will find the direction of magnetic field. Here magnetic field will go back of the wire from right direction and will come in front from the left direction. This will be the direction of magnetic field, and we can draw similar multiple magnetic field lines, and we will get this anti-clockwise like field. Now we have a compass, and which is placed near this current carrying wire. Suppose we have a compass and we have placed it here. Now this compass will get will deflected due to magnetic field of conductor. And where it will point? Now to find out the direction of needle, we have to find out magnetic field at that point. Suppose at this point there is a magnetic field line which goes like this. Here it goes beyond the wire and then it comes like this. And it goes like this. This is a hypothetical line. Now at this point, if we find the direction of the magnetic field, then what we have to do? We have to draw a tangent. So first of all, let's erase this and complete this magnetic field line. Now this is our point of interest where compass is placed. Now if we find the direction of magnetic field here, it will be tangent to this magnetic field line, and this is the direction of magnetic field line. So if we place compass here, then that compass will point like this. It will point in the direction of magnetic field line, and direction of magnetic field line here will be this. So compass will point in this direction. Now, what will happen if we increase the value of current? As we increase the value of current, now this compass will orient it more and more towards the direction of the field, and after certain value of current, when compass has already rotated itself or aligned itself with the direction of field, there will be no further alignment or no further rotation. So in starting, compass will start aligning slowly, and as we increase current, compass will fully align with this applied field, and after some value, alignment will be proper and there will be no further change in direction of the compass. So with this, question number 8 is complete. Now going to question number 9. What is full form of MRI? So MRI stands for magnetic resonance imaging. What is what are its uses? It is used to get images of human tissues. How? In MRI, a strong magnetic field is applied. Is applied on the person. Actually, that person is placed inside a magnet. There is a huge magnet, and that person whose MRI has to be taken, that person is placed inside that magnet. Now, what happens? Due to this huge field, protons inside tissues experience force, and they get excited. Now, when they comes to their normal state, they release energy, and that energy, that light, is used to make an image of the tissue. With the help of MRI, we can get deep tissue images, and with the help of those images, we can diagnose cancers and uh, other diseases which are not possible, as we cannot cut human, or there are some tissues in which inside we cannot go. So with the help of MRI, we can take images of those tissues like mind, like brain, and like heart. This can be only possible with the help of MRI. Now, with this, question number 9 is complete. Going to question number 10. Why two magnetic field lines cross each other? So we have already discussed its solution, that why they cannot cross each other, because at the point of cross section there will be two directions of magnetic field. Because there are two lines crossing, there will be two tangent with two directions, and for a single point we can have only one direction. So two magnetic field lines can't cross each other. Moving to question number 11, state the rule for finding the direction of magnetic field produced around a current carrying conductor, and its answer is the right hand thumb rule. We have already discussed this rule in quite of detail and many times in theory class and in our previous question series also. So you can find its explanation there. Moving to next. Mention the shape of the magnetic field lines around a current carrying straight conductor. So this can be easily, we can find them easily, we have already discussed in question number 8. So suppose we have a conductor, this conductor, and in this conductor we have a current which flows in upward direction. So current is flowing in upward direction. Now to find the magnetic field direction, we will use right hand thumb rule. How we can apply right hand thumb rule here? To apply the right hand thumb rule, uh, you have to point your right hand thumb in the upward direction, and you have to notice movement of your fingers. If your thumb is pointing upward and then you see rotation of your fingers, then you will find that your fingers are rotating counterclockwise when you are seeing from the top. So your field will be rotating counterclockwise, means it will be going from, suppose this is left direction, this is right direction. It will be going from left to right direction behind the line, and then from behind the line it will be coming forward and then going above the line. So this is how your magnetic field will be rotating, and we can draw similarly multiple lines, and these are closed and continuous curves. So that's how you can find out magnetic field lines for uh, long and straight conductor, and shape of these lines is shape of these lines are concentric circles, and they are not equally spaced. Their space keeps on increasing. Concentric circles with spacing between them keeps on increasing with the distance from conductor. This space between these lines will keep on increasing as distance increases, because as we move away from the conductor, the value of magnetic field reduces. So with this, question number 12 is complete. Moving to question number 13. A current carrying conductor is a magnetic field experience a force. Write the condition for this force to be maximum. So, in question number 13, we know that force experienced by current carrying conductor is given by VIL sine theta. And for this force to maximum, for this force to be maximum, sine theta should be 1, because maximum value of sine theta is 1. Implies theta is 90 degree. And what is this theta? Theta is angle between length and magnetic field B, length and B. So it means length and magnetic field of magnetic field applied. So we have to length of conductor and applied magnetic field should make 90 degree angle with each other. And we also know that direction of length is same as the direction of current. Here this I is current. So we can also write that uh, the angle between direction of current and direction of applied magnetic field should be 90 degree. Only then force will be maximum. Only then force will be maximum. So this is the condition for maximum force on a current carrying conductor. Moving to question number 14. Moving to question number 14. Write and state the rule which helps the find the direction of induced current. This is not particularly in your syllabus for CBSE students, but I mentioned the rule of name of the rule, and the rule is Fleming's right hand rule. This rule is used to find the direction of induced EMF. Now moving to our today's last question, question number 15. An alternating current has a frequency of 50 Hz. How many times does it change direction in 1 second? Give your reason and explain why. This we have already discussed a lot. So we have frequency equal to 50 Hz. Now we know if we draw the cycle for 1 Hz wave, 1 Hz or 1 cycle wave looks like this. We have this crust and this is known as trough. So here we have positive, here we have negative. So in this one cycle wave, the wave has changed its direction 2 times. Here one, here second. So in one cycle, wave changes its direction 2 times. And we have heard 50 Hertz wave. 50 Hertz means 50 cycles per second. So in 50 cycles, wave will change its direction equal to 50 into 2, 100 times. So that's how you can find out the answer. Suppose if we are given 60 Hertz, then wave will change its direction 60 into 2, 120 Hertz times. Okay. So with this, our today's video is complete, and we have completed our today's target of 15 questions. And as usual, if you find this video useful, relevant to your syllabus, your context, then please do hit like button, share this video and subscribe to our channel, because your like, your share, your subscription help us a lot. It motivate us, and it is a zero cost way for you to support us. Also do share your valuable feedback. With this, we take leave for now. We will meet in next video with remaining questions, and thanks for watching.